Nikola Tesla emerged as one of the most influential figures in the development of modern electrical technology during the late 19th and early 20th centuries. Born in 1856 and passing in 1943, he dedicated his career to advancing electromagnetic principles that transformed the transmission and utilization of electrical power. His polyphase alternating current system, along with the associated induction motor and transformers, established the foundation for efficient long-distance electricity distribution that continues to underpin global infrastructure. These achievements positioned him as a central architect of the electrical age, enabling the electrification of industries, cities, and households on an unprecedented scale. Tesla's work extended beyond practical engineering into experimental domains, where he explored high-frequency phenomena and concepts for wireless energy transfer, reflecting a persistent drive to expand the boundaries of electrical application. Throughout his career, Tesla demonstrated a pattern of inventive brilliance paired with challenges in commercial realization. He developed numerous devices, including the Tesla coil for generating high-voltage currents and early forms of radio communication and remote control. His experiments encompassed fluorescent lighting precursors, X-ray imaging techniques, and mechanical innovations such as the bladeless turbine and valvular conduit. These contributions, many of which received patent protection, illustrated his capacity to integrate mechanical and electrical principles in novel ways. At the same time, Tesla pursued more speculative projects, including a proposed particle beam weapon and vibrational devices, which remained largely conceptual or limited in demonstration. His approach emphasized independent experimentation, often conducted in dedicated laboratory settings, where dramatic displays of electrical discharges highlighted the potential of high-frequency alternating currents. The historical trajectory of Tesla's endeavors reveals a complex interplay between technical success and unrealized ambitions. While his core alternating current technologies achieved widespread adoption and generated substantial economic value for industry partners, his later visions for global wireless power transmission encountered insurmountable technical and financial obstacles. Professional relationships with key industrialists and financiers shaped the trajectory of his projects, influencing both their initiation and eventual discontinuation. Government examination of his materials following his death confirmed the public availability of his documented work and the absence of any concealed revolutionary devices. Tesla's legacy endures through the pervasive integration of his proven inventions into contemporary electrical systems, educational initiatives at preserved sites, and cultural recognition of his role as a pioneering thinker whose ideas continue to inspire advancements in energy transmission and related fields. The life and career of Nikola Tesla. Tesla entered the world on July 10, 1856, in Smiljan, then part of the Austrian Empire and now located in Croatia, within a Serbian family. His father served as a priest, while his mother exhibited notable mechanical aptitude that likely influenced his early inventive inclinations. From a young age, Tesla displayed exceptional proficiency in mathematics and physics, though his formal education followed an irregular path. He pursued engineering studies at the Austrian Polytechnic in Graz and briefly at the University of Prague without completing a degree. A transformative insight occurred in 1882 in Budapest, where the concept of the rotating magnetic field crystallized, laying the groundwork for his subsequent alternating current developments. These formative experiences cultivated a deep commitment to electrical engineering that defined his professional path. In 1884, Tesla immigrated to the United States with limited resources and initially secured employment with Thomas Edison in New York. The collaboration proved short-lived, ending amid a dispute over compensation for proposed improvements to direct current apparatus. Tesla subsequently established his own firm, Tesla Electric Light and Manufacturing, in 1886, though he soon lost control of the enterprise. By 1887 and 1888, he had refined and patented his polyphase alternating current system and induction motor, innovations that offered superior efficiency for power transmission over long distances compared to prevailing direct current methods. These patents attracted the attention of industrial partners and marked Tesla's transition from employee to independent inventor. His naturalization as a United States citizen in 1891 coincided with a period of his rising prominence in electrical circles. Tesla's career trajectory encompassed both laboratory innovation and public demonstration. He conducted extensive high-frequency experiments in New York laboratories and at a dedicated facility in Colorado Springs during 1899, where he illuminated lamps wirelessly across short distances and produced artificial lightning effects. These activities underscored his mastery of resonant inductive coupling and high-voltage phenomena. Financial difficulties and shifting priorities later constrained his operations, leading him to reside in various New York hotels. Tesla died alone on January 7, 1943, at the New Yorker Hotel from heart failure at the age of 86. His lifetime spanned critical transitions in electrical technology, during which he contributed foundational elements that facilitated the transition to alternating current dominance in power systems worldwide. Major inventions and technical contributions. Tesla's development of the polyphase alternating current system represented a decisive advancement in electrical engineering. This framework incorporated generators, transformers, and motors capable of transmitting power efficiently across substantial distances without the prohibitive losses associated with direct current. The induction motor, a brushless design operating on alternating current principles, emerged as a reliable workhorse for industrial applications and remains integral to modern machinery. Licensing of these patents to George Westinghouse in 1888 facilitated their commercial deployment, culminating in the successful illumination of the 1893 Chicago World's Fair and the operation of the first major hydroelectric plant at Niagara Falls in 1896. These milestones validated the superiority of alternating current for large-scale electrification and established Tesla's inventions as cornerstones of the modern power grid. Additional technical achievements further demonstrated Tesla's versatility. He invented the Tesla coil in 1891, a high-frequency transformer that produced dramatic electrical discharges and found applications in radio transmission and scientific demonstrations. Early experiments with X-ray imaging, which he termed shadowgraphs, predated widespread recognition of the technology, while his work on fluorescent lighting contributed to subsequent lighting advancements. The radio-controlled boat exhibited in 1898 illustrated principles of remote control that anticipated later developments in robotics and wireless guidance systems. Tesla also explored alternating current dynamos and contributed concepts relevant to radar precursors. Collectively, these inventions, protected by approximately 300 patents worldwide, underscored his ability to translate electromagnetic theory into functional devices that addressed practical engineering challenges. The technical legacy of Tesla's inventions lies in their seamless incorporation into everyday electrical infrastructure. The alternating current framework he pioneered enables the reliable delivery of power to homes, factories, and transportation networks across continents. Induction motors drive countless appliances and vehicles, while high-frequency components derived from his coil designs support communication technologies. Although some experimental devices, such as the bladeless turbine, achieved only limited adoption during his lifetime, they highlighted innovative approaches to fluid dynamics and energy conversion. Tesla's emphasis on polyphase systems resolved key inefficiencies in early electrical distribution, permitting the expansion of centralized power generation and distribution networks that define contemporary energy systems. His contributions thus represent enduring solutions to fundamental problems in electrical transmission and utilization. Visionary projects and experimental endeavors. Tesla pursued several conceptual designs that extended beyond established electrical applications into speculative territories. Among these was the Teleforce device, described in the 1930s as a directed energy mechanism intended to accelerate particles or slugs within a vacuum to high velocities, creating a defensive beam capable of neutralizing distant threats. He envisioned this apparatus as a means to establish an impenetrable barrier, drawing power from environmental sources, though no functional prototype materialized. Similarly, his mechanical oscillator, a small steam-powered vibrator developed in the 1890s, generated high-frequency vibrations that he claimed could induce resonant effects in structures. These projects reflected Tesla's interest in harnessing vibrational and high-energy phenomena for novel purposes, yet they remained confined to preliminary demonstrations or theoretical proposals. The Tesla valve, patented in 1920, exemplified his ingenuity in fluid mechanics through a conduit design that permitted unidirectional flow without moving parts. This passive check valve relied on intricate passageways to direct fluids preferentially in one direction, offering potential utility in pumps and microfluidic systems. Tesla also advanced the bladeless turbine, which employed smooth discs to convert fluid momentum into rotational energy with minimal mechanical complexity. Experiments with ozone generation and early wireless signaling complemented these efforts, while his radio-related patents established foundational elements for tuned circuits. Such innovations illustrated Tesla's pattern of deriving practical mechanisms from fundamental physical principles, even as many awaited later refinement or application in specialized fields. Experimental endeavors during Tesla's Colorado Springs period in 1899 produced striking demonstrations of wireless lighting and terrestrial stationary waves. He illuminated bulbs planted in the ground and observed sparks from grounded objects at a distance, relying on resonant inductive coupling within the local environment. These activities informed his broader conceptions of energy propagation through the Earth and atmosphere. While the projects yielded valuable insights into high-frequency behavior, they also highlighted inherent limitations in scaling such effects for practical use. Tesla's visionary designs, though often unbuilt or incomplete, contributed conceptual frameworks that influenced subsequent research in directed energy, vibration technology, and fluid control, affirming his role as a catalyst for innovative thinking in electrical and mechanical domains. The Wardenclyffe Tower and pursuit of wireless power. Construction of the Wardenclyffe Tower commenced in 1901 on a 200-acre site in Shoreham, Long Island. The structure rose to approximately 187 feet, surmounted by a large spherical dome, and featured an extensive underground network of iron rods extending 120 feet into the earth. Designed by architect Stanford White in collaboration with Tesla, the facility incorporated laboratory buildings intended to serve as a central hub for global operations. Tesla conceived the installation as the cornerstone of a world wireless system capable of transmitting both electrical power and communication signals without physical conductors, utilizing the Earth as a conductive medium and the ionosphere as an opposing boundary. Initial funding from J.P. Morgan, amounting to $150,000, supported early phases of the project, with expectations centered on transatlantic radio capabilities. Tesla expanded the scope to encompass wireless power delivery, envisioning the tower as a means to illuminate lamps and energize devices worldwide from a single station. Related experiments at Colorado Springs had already demonstrated short-range wireless lighting through resonant methods. However, escalating costs and competing successes in conventional radio transmission prompted Morgan to withdraw additional support. The project faltered by 1905 or 1906 and never achieved operational status. In 1917, the tower was dismantled for scrap to address Tesla's accumulating debts. The Wardenclyffe site today encompasses the surviving laboratory building, which forms the nucleus of the Tesla Science Center at Wardenclyffe. This facility functions as a museum and educational institution dedicated to preserving Tesla's contributions and promoting science, technology, engineering, and mathematics initiatives. Recent developments include the construction of a new visitor center, enhancing public access and interpretive programs. Although the original tower no longer stands, the location serves as a tangible link to Tesla's ambitions, illustrating both the scale of his vision and the practical constraints that prevented its full realization. Modern recreations, such as a tower constructed near Milford, Texas, by Visiv Technologies, have tested analogous surface wave transmission concepts, yet none have replicated global wireless power at the envisioned scale. Networks, relationships, and commercial realities. Tesla's professional engagements encompassed pivotal alliances and rivalries that influenced the deployment of his inventions. His brief tenure with Thomas Edison highlighted contrasts in business philosophy, as Edison championed direct current while Tesla advanced alternating current. The ensuing competition, known as the War of the Currents, underscored differing approaches to power distribution. In contrast, the partnership with George Westinghouse proved instrumental. Westinghouse licensed Tesla's alternating current patents in 1888, enabling widespread adoption. During a period of financial strain on the Westinghouse company, Tesla relinquished royalty rights, an act that preserved the enterprise but forfeited substantial future income. This decision exemplified Tesla's prioritization of technological progress over personal gain. Financier J.P. Morgan provided critical capital for the Wardenclyffe initiative, motivated initially by prospects of profitable communication services. When Tesla redirected efforts toward power transmission, which presented metering difficulties, Morgan declined further investment. Personal connections enriched Tesla's social sphere. Author Mark Twain maintained a close friendship, visiting laboratories and sharing intellectual exchanges that mutually influenced their respective fields. Tesla also associated with editor Robert Underwood Johnson and his wife Catherine, whose salons introduced him to literary and scientific luminaries, including figures such as Rudyard Kipling and John Muir. Inventor John Jacob Astor offered additional financial backing, while Tesla's nephew Sava Kasanovic later managed aspects of his estate. Commercial outcomes from Tesla's inventions revealed both potential and limitation. The alternating current system generated significant wealth during its initial licensing phase, briefly elevating Tesla to millionaire status through royalties equivalent to millions in contemporary terms. Patent valuations reached $12 million around 1907, underscoring the economic promise of his core technologies. Yet Tesla's reluctance to engage in sustained business management, combined with generous concessions and ambitious and profitable projects, resulted in persistent financial instability. By his final years, he resided in modest hotel accommodations amid mounting debts. These dynamics illustrate how Tesla's inventive focus often diverged from the commercial strategies required for sustained prosperity, even as his patents delivered immense value to partner organizations and society at large. Posthumous examination, legacy, and contemporary engagements. Following Tesla's death on January 7, 1943, the United States Office of Alien Property Custodian assumed custody of his documents, equipment, and personal effects amid wartime security considerations. The Federal Bureau of Investigation participated in related inquiries, though direct seizure authority resided with the Alien Property Office. Electrical engineer John G. Trump, affiliated with the Massachusetts Institute of Technology, conducted a review of the materials and concluded that the later writings consisted primarily of speculative and promotional content, containing no novel, practicable principles for revolutionary devices or weapons. The majority of the papers were subsequently transferred to Tesla's nephew and ultimately to the Nikola Tesla Museum in Belgrade, Serbia, with select portions declassified over time. Certain items remain unaccounted for, attributable to archival inconsistencies rather than deliberate concealment. Tesla's documented work resides fully in the public domain through patent records, museum holdings, and archival repositories. No verifiable evidence supports the existence of functional, concealed technologies capable of generating substantial undisclosed value. All major inventions, including the alternating current framework and associated components, have undergone extensive exploitation and refinement by industry, yielding trillions in aggregate economic benefit. Attempts to replicate elements of Tesla's experimental infrastructure, such as surface wave towers, have occurred in contemporary settings but have not achieved the global transmission objectives originally proposed. The Tesla Science Center at Wardenclyffe continues to operate as an educational and commemorative institution, offering tours, exhibits, and programs that engage the public with Tesla's historical contributions and foster ongoing scientific inquiry. The enduring legacy of Tesla manifests in the pervasive presence of alternating current systems that supply electrical power to the modern world. The International Unit of Magnetic Flux Density bears his name, symbolizing recognition within the scientific community. Cultural representations portray him as an emblem of inventive independence and forward-thinking imagination. Educational facilities dedicated to his memory, including the Belgrade Museum and the Long Island Science Center, preserve artifacts and promote awareness of his achievements. Although ambitious projects such as universal wireless power transmission encountered fundamental physical and economic barriers, Tesla's verified innovations established the infrastructure for electrification that defines contemporary civilization. His career exemplifies the transformative potential of focused technical creativity, even when tempered by practical constraints, ensuring that his foundational contributions remain integral to electrical engineering and energy distribution. Conclusion: Tesla's enduring legacy in electrical technology and innovation. Nikola Tesla stands as a pivotal architect of the electrical era whose polyphase alternating current system, induction motor, and associated technologies established the essential infrastructure for global power distribution. His inventions, protected through extensive patent portfolios, transitioned from laboratory demonstrations to foundational elements of modern electrification, powering industries, cities, and transportation networks worldwide. The alternating current framework resolved critical inefficiencies in long-distance transmission, while devices such as the Tesla coil and remote-controlled mechanisms extended the reach of electromagnetic applications into communication and control systems. Tesla's career trajectory, marked by periods of intense innovation in facilities like Colorado Springs and Wardenclyffe, reflected both remarkable technical insight and the practical challenges of scaling visionary concepts. Through partnerships that included licensing agreements and experimental collaborations, his core contributions achieved commercial realization and enduring integration into contemporary engineering practices, generating immense societal and economic value despite his personal financial difficulties. The ambitious endeavors that characterized Tesla's later work, including proposals for wireless power transmission and directed energy devices, illustrated the scope of his imagination even as they encountered insurmountable barriers related to efficiency, funding, and physical realization. Projects such as the Wardenclyffe Tower embodied his pursuit of a unified global system for energy and communication, yet remained incomplete due to economic constraints and technical limitations inherent in large-scale resonant propagation. Posthumous review of his materials by government authorities confirmed the public accessibility of his documented inventions and the absence of any concealed revolutionary technologies. Tesla's network of relationships with industrialists, financiers, and intellectual contemporaries shaped the implementation of his ideas, highlighting the interplay between inventive genius and commercial realities. Educational institutions dedicated to his memory, including the Tesla Science Center at Wardenclyffe and the museum in Belgrade, preserve these elements and promote continued engagement with his principles through exhibits, programs, and historical interpretation. In retrospect, Tesla's legacy resides in the pervasive influence of his verified achievements on electrical infrastructure and in the inspirational quality of his forward-looking visions. His life demonstrates the transformative power of focused electromagnetic research alongside the constraints imposed by economic, physical, and organizational factors. The alternating current systems that define power delivery today, along with derivative technologies in wireless charging and high-frequency applications, attest to the lasting impact of his foundational work. As preserved sites and cultural representations continue to highlight his contributions, Tesla exemplifies the role of the independent inventor in advancing human technological progress. His story underscores the enduring significance of integrating theoretical insight with practical engineering, ensuring that his documented innovations remain central to the operation of modern civilization and the ongoing exploration of energy-related advancements.